In this video, we are going to talk about per VLAN spanning tree configuration. We are going to talk about the configuration that may affect the route elections, the port role decisions, and finally we are going to explore the timer configurations. First, let's take a look at some of the basic configuration for the spanning tree. By default, all Catalyst switches are going to come pre-configured with the per VLAN spanning tree. The PVST is going to be enabled on all the configured VLANs up to a platform maximum. The platform maximum is the number of instances of spanning tree that a particular switch can run. Depending on which platform you're using, this could be a relatively low number like 128 instances or 256, and in some cases it could even be all 4094 VLANs. As I say, this is very platform dependent. By default, spanning tree is going to be turned on all the VLANs, but you can turn it off. The command to do that is no spanning tree VLAN and then the VLAN ID on which you want to turn off the spanning tree. We can also decide which mode of spanning tree we wish to run. Is it going to be the PVST, the default one, or rapid PVST, or the MST? And lastly, globally, we can configure logging of some important spanning tree events. Let me show you these couple of things. So here I have my Cat1 and Cat2, and I'm just going to first see what am I dealing with. The command to take a look what is happening spanning tree wise on your switch is show spanning tree. Show spanning tree, you're going to see an overview of the configuration for the spanning tree for all the VLANs. Now here I see that only VLAN number 1 is configured. I can see here that the information displayed is for VLAN 1. I can see that the spanning tree is enabled and it says protocol is IEEE. The IEEE is Cisco's way of saying that this is actually running per VLAN spanning tree. Also, here in this segment of the output, I have the information about the route bridge. Also, in a case that the switch on which I'm looking at the output of this command is the route, I'm going to see the information that this switch is the route. Also here I'm going to see the configured parameters for my timers. I can see that the hello time is 2 seconds, the maximum age is 20 seconds, and the forwarding delay is 15 seconds. This is the information propagated by the route. In this case, this is us. Finally, here I have the information about the local configuration. What is my own bridge priority? What is my bridge address? The hello time, the maximum age, the forwarding delay, and the aging timer. Now, the aging timer is important, and you may recall this timer when we talked about the topology changes in our network. The default aging timer, the default MAC address aging timer on Catalyst switches is 300 seconds. When there is a topology change bit set in a configuration BPDU sent by the route switch, this timer here will change to be the same value of the forwarding delay. So now we can see that on this switch we have actually a stable topology. There is no TC bit set anywhere because our aging timer is not actually the same as forward delay. In the output below, I can see on which interfaces the spanning tree is running. I can see that I have it running on 2 ports, Fast Ethernet 03 and Fast Ethernet 024. I can see that both of these ports are designated ports, which is to be expected when the switch is the route. I can see that the status is forwarding, that the cost is 19, which is the default for 100 meg interfaces, and I can finally see here the information about the priority and what type of interface we are dealing with. Now, the type of the interface here is something that I haven't talked about yet, because this is really a concept from the rapid spanning tree. I will talk about it when I talk about the rapid spanning tree. Let's now take a look at what happens if we have more than one VLAN configured on our switches. So I'm going to go to Cat1 and I'm going to create a couple of VLANs. So now I have 5 VLANs that are configured. I have VLANs 1 through 5 And then I have these 4 default VLANs, but I'm not going to see them in the spanning tree because these are not Ethernet VLANs. So if I do show spanning tree, the same command that I was running now, I'm going to see that I'm still seeing only the output for VLAN 1. The reason for that is that the link, that this is the only VLAN active on any of the links on my switch. The reason for that, of course, is that I don't have any trunks, or I have not assigned VLANs manually to any interfaces. So if I take a look at, for example, show spanning tree VLAN 2, it is going to tell me that the instance for VLAN 2 does not exist. The switch is not going to create a VLAN, the spanning tree instance for the VLAN that is not in use. So let's bring some of these VLANs into use. I have a link connecting Cat 1 to Cat 2, and it's fast Ethernet 24. So I'm going to go to this interface and I'm going to change it to be dynamic desirable. I want to negotiate the trunk on this link. When I do this, and when the interface changes state to up, if I do show spanning tree, what I'm going to see now is a much longer output. I can see that I have the same summary information that I was seeing before for each of my VLANs. Finding information about a particular VLAN in this huge output that I had here may be a little bit challenging. So what I can do instead is do something like show spanning tree VLAN 3, for example. And now I'm going to see the information only about VLAN 3. And this is where I'm going to show you the first difference in the output. Let me show you the output for VLAN 1 and for VLAN 2, for example. Take a look at the root priority here and the root priority here. You can see that the value is 32,770 for VLAN 2, and it is 32,769 for VLAN number 1. The reason for that, of course, is the use of the system extended ID, or the extension of the system ID. When we are using per VLAN spanning tree, we need to identify the bridge in all of the VLANs, and this ID needs to be different. There are 2 possible approaches for this. One is to use the same priority everywhere, for example 32,768, and then use a different MAC address for all the VLANs that we create. But this would be a terrible, terrible waste of VLAN space, because of the MAC addresses, because MAC addresses are a finite resource. So instead of doing that, Cisco opted for extending the system ID to extend the priority in such a way to add a VLAN ID to the priority to uniquely identify the bridge, even though it has the same base priority. What I mean by this is, here we can see that the base priority for this VLAN, and this is VLAN number 1, is 32,768. But we have the extended system ID is 1, which means that the resulting priority is 32,769. In the case of VLAN 2, what we have is the base priority of 32,768 and the extended system ID of 2, which results in the actual priority that will be used of 32,770. So that's the extended system ID. This is actually configured on all Catalyst switches, and if I do show run include spanning tree, I'm going to see it in the configuration. So this is the configuration that is always there. And you know what? It cannot be removed. If I try to remove this option, I'm going to be met with a warning message informing me that this is not possible to be done. Going back to finding the information in the output, you remember that I said if we do show spanning tree that our output here is going to be very, very long, and finding information may be a little bit difficult. I can actually find more condensed information about my local config if I do show spanning tree bridge command. This is going to give me a very quick overview of how spanning tree is operating on my local switch. As I can see there, I have the information about the VLAN, I have the information about the local bridge ID, I can see the effective priority, and I can see the base priority and the extended system ID in brackets there. I can see which MAC address is being used for the bridge MAC address. I can see the configured timers, and finally, which protocol is in use. So very useful command to see a quick overview. I also have the option to use show spanning tree summary. This will give me even more condensed information about the global configuration of the spanning tree, like for example, in which mode the switch is operating. Am I the root bridge for some VLANs? And here I'm informed that I'm root for VLANs from 1 through 5. Is extended system ID in use, and is, are some of the more advanced spanning tree features turned on? I will talk about all these features in a moment. And then finally, here I have information about what kind of path cost method is used. Path cost method, and let me show you this in the configuration. So I have spanning tree path cost method. I have two options. I have long or short. And this is actually how many bits I'm going to use from the cost to calculate the overall path to the root. I will talk more about this when I talk about the rapid spanning tree. These commands gave me information about locally configured parameters. But let's take a look at the information about the root. I can also use show spanning tree and then scan in my VLAN output here for VLAN 1 and then for VLAN 2, for VLAN 3 and so on. I can scan for the information about the root bridge. But I can also use the command show spanning tree root. With show spanning tree root, I'm going to see a very quick condensed information about all the VLANs and about information about the root. In this case, I am the root, but it doesn't matter. The switch is still going to show me these parameters. But one thing I cannot see here, you see the last column here, it says the root port. Because I'm observing this on a switch that is the root itself, there are no root ports, because all the ports on the root bridge will be designated ports. Let's switch to Cat2. So on Cat2, I don't have additional VLANs configured, so let me quickly configure VLANs from 2 to 5 so that I can enable spanning tree on them. And finally, I'm just going to say show spanning tree root. Now, if I take a look at show spanning tree root, I'm going to see pretty much the same information that I've seen on Cat1, except now I'm informed in a nice and condensed way which port on the local switch is actually the root port facing this particular root. In our very complex topology of two switches interconnected with a single link, this is not very useful information. But if we had more complex topology, if we had multiple links, finding out what is the root port for a particular VLAN very quickly is a useful information. Another thing that I can use with show spanning tree root command is I can see more detailed information. So this output may look familiar. If I do show spanning tree VLAN 1, for example, take a look at this information in the header here. This is pretty much the same information that I'm going to be getting here. Almost all. I'm not going to see the hello parameters. Actually, I am, sorry. I was looking at the wrong output. So here it is. It's basically the same header here. So with show spanning tree root detail, I can see those parameters more expanded. Also, I can see the information about the root ports. If this is the only thing that interests me, I can do show spanning tree root port, and I'm going to get even more condensed information about the root ports. In all the show examples so far, I have focused on showing you condensed information. But what if I wanted to look at the information in greater detail? Well, spanning tree offers that as well. If I do show spanning tree, let's say VLAN 1, detail, what I'm going to get is a very detailed information about spanning tree in VLAN 1. Let's take a look. This is divided in two sections. The first is the global information about how spanning tree operates on this switch in VLAN number 1, and then I have a section that details port-related operations. So for each port in this VLAN, I'm going to get very detailed information how spanning tree operates in that VLAN on that port. So let's go back to this output above here. I can see the first line tells me that VLAN 1 is operating in IEEE compatible spanning tree protocol. Remember, in Cisco world, on Catalyst switches, this means it's operating in per VLAN spanning tree mode. I can see what is my bridge ID. I can see what is the configured hello time. We can see who is the root, and in this case it says we are the root. Let me show you the same output on Cat2, which is not the root. So I'm just going to say show spanning tree VLAN 1 detail. So here, instead of telling me that I am the root, what Cat1 said, Cat2 is informing me what is the current root, what is the address, and what is the priority, and also I will have the information about the root port. The next line here, now I'm back on Cat1, is telling me that the topology change flag is not set. That means that topology is stable, nothing is going on there. And then finally, I have some information about when was the last time the topology change has been seen. And I can see here information about how many times certain things have happened and what are the actual timers. The information about the port, here what I can see is, and this is interesting, it says here port number 5 and port 26, and then in parentheses I have the actual port number in use. The reason why I'm seeing this is that port 1 is not necessarily going to be fast Ethernet 01. On fixed platforms, on fixed configuration platforms, like for example the 3560 that I'm using, the port number 1 can be either the first fast Ethernet interface or the first of the uplink interfaces. The 3560 that I'm using has two uplink interfaces, two gigabit interfaces, gigabit 1 and gigabit 2. These are, on this platform, ports number 1 and 2. Fast Ethernet 01 will be port 3, Fast Ethernet 2 will be port 4, and Fast Ethernet 03 becomes port number 5. Similarly to this, Fast Ethernet 24 is port 26. This is just internal numbering on the switch, but this is nevertheless something that you can see with the spanning tree. In the case of modular platforms, like for example 4500 series switches or 6500 series switches, the port order depends on where in the switch the line card with ports has been inserted. The supervisor ports are going to be the first ports in the series, then the redundant supervisors if you have redundant supervisors, and then line cards usually in ascending order of slot numbers. So slot 1 will probably have ports that are lower in numbering than, for example, slot 2 in the switch. The next information that we can see here is how the port operates. What is the state of the port? Is it blocking? Is it forwarding? Is it learning? Is it listening? And here we can see that this is a designated port and that it is actually in forwarding state. Finally, I have the route path, the path cost. Here, this is the actual configured cost on the interface derived from the bandwidth. I have the configured port priority and what is the port identifier. And as you can see, the port identifier is the combination of the actual port priority, which is 128 by default, and the actual port number 5. So here, for example, for Fast Ethernet 024, I have port identifier, the composite value that consists of the priority 128 and the port ID 26. And this is why it's important to know that the port 24 may not necessarily be port ID 24 in a case that you are looking at why certain port has moved into forwarding state or blocking state. And I'm going to talk about it in a moment when I'm going to discuss how to influence those decisions. And finally here, I have the information about the designated port. I can see the designated route, what is the priority, what is the designated bridge, and these are all going to be local values because this switch is the designated, it has the designated port on the segment here. Let's take a look on Cat2 on port FAST24. So if I take a look at this output here, I will see that this information about the designated route and the designated bridge, these values here are going to be the same as I'm seeing on Cat1. So take a look. It says here that the designated bridge has this priority and this address. I'm going to switch to Cat2 and see that these are the same value. I'm just going to highlight the MAC address. The reason why these are the same is because this interface, FastInternet24, is what interconnects Cat1 and Cat2. And there can be only one designated port on this segment, and it will be the one on Cat1 because Cat1 is closest to the route. The route cost is 0 from Cat1's perspective. And finally here I have also information about the designated port ID. Again, these values will match on Cat1 and Cat2 and they will be those of Cat1. And finally, I have some information about the timers and different counters in place there. So this is the detailed information about the spanning tree operations on the switch. What if I wanted to see similar information but displayed only for the interfaces? Well, I have that option as well. I can say show spanning tree interface and I can say on which interface I want to see this information for, and if I press just enter, I'm going to get a summarized output here. So I'm going to get the information of how spanning tree operates on this particular interface in a summary form. As you can see, this is a very similar output to the one from show spanning tree. It's basically this information here, somewhat condensed, right? So if I do show spanning tree interface here, I'm just going to get the information for which VLANs is the spanning tree operating on this port and what are the parameters, what are the current port roles, the status, what is the cost, the priority, what is the port number, and what is the type. Again, I will talk about type when I talk about the rapid spanning tree. Another thing that I can do here is if I, for example, want to see just the information about the cost on this port, and I will get the information about the VLAN. And this brings me to another point. I talked about cost so far that it is derivative value from the port bandwidth, but it can also be configured manually, and that can be done actually per VLAN. I don't have to configure it for all the VLANs. So I can have a different cost for VLAN number 1 and VLAN number 5, for example. Also, I can see the detailed information, and this here should look very familiar. This is the similar output to the one that we just explained like 2 minutes ago, except now I'm going to get this information on a per port, not per VLAN basis. So here I have the detailed information how each of the spanning tree instances on FastInternet24 are operating on that port. Again, this will be the same output as the one I explained earlier. What other options do I have here? I can see what is the port priority, again, condensed information just per port. And finally, I can see the information about the state. Also, I can see what is the cost to reach the route out of this port. And as you can see, because Cat1 is the route itself, the cost is 0. Now, when we know how to collect the information about spanning tree, let's take a look at the actual configuration of the spanning tree. The first command that I'm going to introduce is the command that we can use to change the spanning tree mode of operation. It's the spanning tree mode. With the spanning tree mode, I have 3 possible options. I can run MST, the PVST, or the rapid PVST. The PVST is the default, and when I type this command in, I'm going to change the running operational mode of my spanning tree to PVST. In other words, absolutely nothing happens because this is exactly what I was running up to this moment. The next command I'm going to show you is spanning tree logging. I'm going to do this on cat2. So I'm going to go to the terminal and I'm going to say spanning tree logging. This command will cause the switch to log to configured destinations important events about the spanning tree, like for example when the interface changes state to down. So I'm going to go to fastEthernet03, which is just an interface connected to a host on cat2, and I'm going to shut it down. When I shut it down, I'm going to see now the log message which informs me that there was a topology change in my network. Let me make a more significant change here. I'm going to go to cat1 and I'm going to shut the interface down between cat1 and cat2. When this happens, what's going to happen on cat2 is that I will have no spanning tree instances running. Let's configure fastEthernet03 to actually be operational. When this happens, what's going to happen is that cat2 is going to think it's the root in our spanning tree domain. Let's make cat1 the root. How am I going to do this? Well, by just bringing up the interface between cat1 and cat2. When this interface comes up, let me clear the screen, what's going to happen is that I'm going to get the notification from my spanning tree logging that I have a new root port because the root has changed. I'm also going to get some topology change notification as well. Turning off spanning tree for a particular VLAN is a very, very simple thing to do. All I have to do is, on my switch, do no spanning tree VLAN 3, for example, and if I do show spanning tree bridge, here I will see that my spanning tree is now running only for VLANs 1, 2, 4, and 5. There is no trace of VLAN 3. If I do show spanning tree VLAN 3, I'm going to see that there is no instance of spanning tree running in VLAN 3. These were the basics of configuring the per VLAN spanning tree. Now let's go a little bit deeper and explore how can we actually manipulate the configuration of the running spanning tree, how we can affect the root elections and port role selections. We know that root election in spanning tree is the process that is affected by two values. It is going to be bridge priority and, of course, the bridge MAC address. Bridge MAC address is the value that is pre-configured on the switch. There is nothing we can do about that. So affecting root elections is going to be a factor of manipulating the bridge priority. This can be done using several mechanisms. We can set this value manually, or we can let the switch decide what to do. Let me show you. If I go to my terminal here, and if I do show spanning tree, I will see that the current bridge priority is the default 32,768. And of course we have the extended system ID. Again, this is something that I cannot do anything about, which results in the bridge priority of 32,769. So this is the configuration on cat1. This is the configuration on my cat2. I can see pretty much the same values, but cat1 ended up being the root because of the lower MAC address. This is the MAC address in use by cat2, and this is the MAC address in use by cat1. And I can see that this value here, 0019060C, is actually lower than 0019017. So I can see here that because of this 0, cat1 wins. So how can I make cat2 become the root? Well, it's very simple. I'm just going to go to the config terminal, and I'm going to say spanning tree and question mark. when I'm configuring per VLAN spanning tree, I need to configure this, as the word implies, per VLAN. So I'm going to put the VLAN keyword here, and here I need to specify the range of VLANs. Let's make change just for VLAN number 1. So I'm going to say spanning tree VLAN 1, and here I have the option to set the priority. And the priority can be set only in increments of 4096. If I try to set it to, for example, 33, I'm going to get a very friendly reminder from my cat switch telling me that I have to use one of these values here. So the default value is 32,768, and we know that the lower value wins. So let's make cat2 become the root by choosing the next lower value here. If I do this, what's going to happen is that cat2 is very quickly going to become the root. If I do show spanning tree VLAN 1, I'm going to see here the information that this bridge is the root. So I have done this. This was a direct change of the priority. But there is a way to influence this in slightly indirect way. If I go to cat1 and if I do spanning tree VLAN 1, I had the option to set the root parameter. The root parameter has two sub-options, primary or secondary. If I say root primary, what's going to happen on cat1? It's going to examine the current value of the priority, of the root priority, and the current value of its MAC address, and then it's going to make a determination what to do to become a root. It's either going to make the current priority configured on its own bridge priority. It's either going to make it the same as the current root, or it's going to make it a little bit lower in order to influence the decision. This is something that is not going to end up in the running config. So if I press enter here, and if I do show run include spanning tree, I am not going to see this command anywhere in my running config. What I'm going to end up seeing is the actual calculated priority based on the algorithm that has changed over time in different iOS versions. So the important thing here to remember is that this command here, spanning tree VLAN x root primary, is actually a macro. It will be expanded into something else and not end up in a running configuration. But the end result is the same. cat1 is now back being the root. So if I do show spanning tree, I will see that this bridge is the root. It's important also to understand that there is no endless recalculation as the result of this command. That means that if I go to cat2 and I repeat the exact same command, spanning tree VLAN 1 root primary, now cat2 is going to become the root. The result of this configuration on cat1 of me typing this command in is not that cat1 is always going to keep on trying to become the root. It's the calculation that happens only when I actually press enter. But let's confirm that cat2 now is the root. So if I do show spanning tree for VLAN 1, I can see that cat2 is now the root. And I can see that the priority is 20,481. If I repeat the same configuration on cat1, I will see now that cat1 has become the root. But the important thing to notice here, and I'm going to show you this right away, take a look at the priority as it was configured on cat2 as the result of this macro. The priority was 20,481. This is going to end up being the same priority on cat1. And this is the beauty of this algorithm. You see, now cat1 determined that if it sets the priority to the same value, it is actually going to win because its MAC address is lower. But this also shows us the limitation of affecting root elections. Let me show you what I mean by that. I'm going to go on cat1 and I'm going to say spanning tree VLAN 1 priority 0. This is the best priority. It doesn't get any better than this. So if I do show spanning tree here, I will see that this bridge is the root and the priority is going to be 1, which is 0 plus the extended system ID for VLAN 1. If I go to cat2 and I say spanning tree VLAN 1 root primary, take a look at this. it is going to tell me that it failed to make this switch a root. Why? Because the only thing that this command can do is set the priority to 0 now. And if it sets it to 0, MAC address of cat1 will be lower than the MAC address of cat2. There is really nothing we can do in this case, other than increasing the priority on cat1, allowing cat2 to win on priority alone. Let's take a look at possible configurations we can use on our switches to affect their port role choices, their port role decisions. To do that, I'm going to slightly modify the topology we are using in our network. So I'm going to use two switches, cat1 and cat2. These are the same two switches I've been using so far, and instead of just having one link between them, I'm going to have two links. This is going to be Fast Ethernet 23, and this is going to be Fast Ethernet 23. This is going to be Fast Ethernet 24, and this is going to be Fast Ethernet 24. Now remember that in our network, cat1 ended up being root. That said, that means that Fast Ethernet 23 here will be a designated port, and Fast Ethernet 24 will be a designated port. But what would be the port states here on Fast Ethernet 23 and 24? Well, let's take a look. Once the BPDUs are received from both 23 and 24, we are going to go through that list of tiebreakers. You remember that the first thing will be the root's bridge ID, and the lower one will win. Then we are going to look at the lowest path or the lowest cost to the root switch. So lowest cost to root. Then we are going to have the lowest sender bridge ID. And finally, we are going to have the lowest port ID that will be taken into account. In our case, the root bridge ID will be the same. The cost to root, given that these are the default costs, that I haven't changed anything there, is going to be the same. The sender bridge ID in this case will be the same, which is the cat1. So finally, we are left with this last tiebreaker, the lowest port ID. Port 23, you may recall, will have the port ID of 23 plus 2, which will be 25, and this one here will be 26, which means that it's very likely that 23 here will end up forwarding and 24 will end up blocking. Let's confirm that. So I'm going to go to my terminal, and first thing that I'm going to confirm is that I have the connection between the two switches, and here I have them. From cat1, I can see cat2 on two interfaces. Let's go to let's do it on cat1. I'm just going to say show spanning tree VLAN 1. Now, because this bridge is the root, all of my interfaces will be designated and forwarding, and this is exactly what I expected to see. On cat2, if I do show spanning tree VLAN 1, I can see here that Fast Ethernet 23 is the root port, which is what we expected to see and is forwarding, and Fast Ethernet 24 is in a blocking state. It actually has an alternate port role. And again, this is something from the rapid spanning tree that I haven't mentioned before, and I will talk about this when I talk about the rapid spanning tree. This is actually not a port role that exists in the traditional spanning tree or in a per VLAN spanning tree, but nevertheless, because the switch has the code to support these different port roles and to support the rapid spanning tree, it is going to show us here that if this was a rapid spanning tree running on this switch, this would be an alternate port. So this is what we expected to see. And I can see that my port priorities here are 25 and 26. So what if I wanted to actually have this reversed? What if I wanted to have actually my port 24 to be forwarding and to have port 23 to be blocking? How would I go about changing this? Well, I have to look at the tiebreakers. I have to look at the algorithm that is being used. Can I change the bridge ID? I cannot. I cannot change the root bridge ID. If I change it, the topology will change. And nevertheless, in my network, I only have 2 switches. So the only solution for this problem would be to make Cat2 a root. So I'm not going to do that. Can I change the cost to reach the root? Of course I can. How can I manipulate the cost on the switch? Well, I can either change the perceived bandwidth or I can change the interface speed. Let's try one of these. But where should I do it? Should I do it on Cat1 or should I do it on Cat2? Well, if I do it on Cat1, that means I need to change these interfaces here. And the cost in this case, when the frame is sent to Cat2, will be 0, because what is being sent in a frame is the sender's cost to reach the root, and because Cat1 is the root, the cost will be 0. Changing the bandwidth or cost or speed of these interfaces will have no effect. If I'm to manipulate the bandwidth to change the election, in this case, to change the port role selection, I would need to manipulate these 2 ports here. So let's go to Cat2 to fast Ethernet 24, and let's change the speed to 10 megabits per second. Now, this is a very drastic change because the interface needs to go down and it will need to come back up. So now that the interface is up, if I do show spanning tree VLAN 1, what I'm going to see here, well, actually I ended up doing the exact same thing. I actually have to do it on fast Ethernet 23. I'm so sorry about this. So I'm just quickly going to change this. I'm just going to say speed auto on 24 and interface fast Ethernet 23. I'm just going to say speed 10. So now with this correct configuration, let's wait for the logging to calm down a little bit. If I do show spanning tree VLAN 1, what I'm going to have now is that fast Ethernet 23 ends up being blocking and fast Ethernet 24 ends up being the root port. And now it's transitioning to a listening phase, it will go into learning phase, and eventually it will go and become forwarding. And you can see here that the cost of this port here is now changed to 100, which is the default cost for 10 megabits per second. But this was a very drastic change. Can I make this change without actually changing the actual speed of the interface, which is what I've done now. If I take a look at show interface here, I will see that the actual speed is 10 megabits per second. Can I somehow accomplish the same thing without changing the speed of the interface? Yes, I can. Let me go back and undo my change. So on fast Ethernet 23, I'm just going to say speed auto and make sure that it returns to 100 megs. So if I do show interface fast Ethernet 23, I can see now that it's back to being 100 megs per second. And instead of changing the actual speed of the interface, what I'm going to do is I'm going to change the logical perception of the bandwidth using the bandwidth command. Let me show you something before I make the change. So show interface fast Ethernet 23. Take a look at this value here, the bandwidth, and it says 100,000. This is the logical configured bandwidth on the interface using the bandwidth command. On Ethernet interfaces, by default, this is derived value from the actual interface speed. So if I change the bandwidth with the bandwidth keyword, I'm just going to change the logical perception of this interface for the protocols that are using this value. The protocols that are using this value are, for example, ether channels or spanning tree or routing protocols like OSPF or EIGRP. So if I change the bandwidth now with this logical configuration, I should affect my spanning tree cost. Before I do that, let's first see and confirm that fast Ethernet 23 is now forwarding and fast Ethernet 24 is now blocking. This is what I expected. So let's change the bandwidth here from 100 megs, let's change it to say 50 megabits per second. So if I do show interface fast Ethernet 23, What I see here is that interface speed remains the same. It's 100 megabits per second, but the logical bandwidth configured on this interface has now changed to 50,000 kilobits per second. Let's see the spanning tree. If I do show spanning tree, VLAN 1, now what I can see here is that FastInternet24 is now a root port. Again, it's going through the phases and just now changed state to forwarding. I can see that FastInternet24 is forwarding, and FastInternet23 with its cost 35 derived from the bandwidth is now in the blocking state. Using the bandwidth to manipulate the spanning tree decision is less intrusive than changing the interface speed, but it's still somewhat intrusive because remember, there are other protocols that rely on this value to calculate their own operating parameters, routing protocols being one of them, and also some QoS operations on the switch or a router in a case that you're doing this on a router. This is something that you may want to avoid. So how can I affect the decision made by the switch without actually manipulating the perceived bandwidth of the interface? Before I do any of that, let me return the bandwidth to its default value. So now I have returned the bandwidth on FastInternet23 to be the default. So if I do show spanning tree VLAN 1, what I should be seeing is that FastInternet23 is now going through its motions to become forwarding, and FastInternet23 is already blocking. I can manipulate the cost using the spanning tree cost command. I can configure spanning tree cost, and then I can set any cost that I like, and this will, in a case of per VLAN spanning tree, apply to all the VLANs. But if I want to manipulate only the decisions made for an individual VLAN, what I can do is on an interface I can say spanning tree VLAN, VLAN number, and then specify the cost. In this case, this change of cost will apply only to this particular VLAN. So let's change the cost on FastInternet23 interface from 19 to 20 for VLAN number 1. If I do show spanning tree VLAN 1, do show spanning tree VLAN 1, what I should be seeing now is again a reversed operation, that FastInternet24 is now root port and FastInternet23 is now blocking port, and I can see that the cost value here changed to 20. But if I take a look at the configuration for VLAN 2, I see that for VLAN 2, actually, there is no change. FastInternet23 is the root port and FastInternet24 is the blocking port. So I can see that my change affected only a single VLAN. Manipulating the cost on the receiving switch is just one way of manipulating the decision made by CAT2. As you can see, lower cost to the root is second option. The third option is the lowest sender bridge ID. Our sender bridge ID will in this case always be CAT1. There is nothing we can do about that, but what we can change is the lowest port ID. Let's go back to our terminal, and what I'm going to do now is I'm going to change everything back to default. So if I take a look at the configuration of FastInternet23 and 24 on CAT2, I'm going to remove this configuration here. I'm going to remove the spanning tree VLAN 1 cost 20. So if I do show spanning tree here, I should see back 23 as being the root port and FastInternet24 as being the alternate port or being the blocking port. Now I'm going to go to CAT1. If I want to make sure that CAT2 is preferring link FastInternet24 over FastInternet23, I need to make sure that the advertised port ID from FastInternet24 is actually lower than FastInternet23. By default, this is the combination of the priority, the default one being 128, and the port ID, 25 and 26. I cannot change the values 25 and 26 because these are fixed based on the port location in the switch. But what I can modify is the actual port priority. So going back to my Cat1, on FastEthernet 23, what I can do is spanning tree, and again, here I have the option to change the port priority for all the VLANs, or I can change only for a single VLAN. So if I change the priority on FastEthernet 23 for VLAN 1 to, let's say, 129, well, I cannot do that, it needs to be in increments of 16. If I change it to, for example, 144, if I go back to Cat2, and if I do show spanning tree VLAN 1, what I'm going to see now is that FastEthernet 23, it should be changing soon. Let's see. There we go. It just started changing now. There was a log message. I was a bit too quick to look. Let me repeat the show command. So now FastEthernet 24 has changed status to listening, and FastEthernet 23 is now blocking. But here, what I'm seeing is the priority is still 128. Well, these are the local values. If I take a look at show spanning tree interface, or let's do show spanning tree VLAN 1 interface FastEthernet 24, let's take a look at the details. What I'm going to see here is this line where I have the information about the designated port ID. This is the designated port ID on Cat1. The designated port is on Cat1. So this is for port 24. What about for port 23? And here I can see my newly configured value 144. If I'm looking on Cat2's side. If I'm looking from Cat1's perspective,